All right, well, we'll get started here. Let me start by welcoming everyone to today's CERIAS Security Seminar. We're going to run this as usual. We'll have our guest present. If you have questions, please put them in the Q&A, and she'll either answer them as they come in or we'll answer them at the end of her prepared remarks. So please don't use the chat. Remember, use the Q&A. And speaking of our guest, it is with great pleasure that I introduce Leslie Carhart. Leslie is well known in parts of the community for her work in not only in IT response, working for Dragos, and before that with Motorola, but also she is a frequent speaker and she says minor celebrity at a number of conferences and workshops throughout the country because of her work. She also has had a 21-year career working as an Air Force reservist with work in incident response and has a particular affection for helping veterans get involved in this field and students. So without much further ado, let me just say again that we're really pleased to have Leslie here, and we'll turn it over to you, Leslie.
Thank you so much. I'm really honored to be here. Thank you everybody for joining today. And I hope that this lecture is useful to a lot of you. This is my sales pitch for you all. I really want you to get into my field. And there's a lot of different areas of that field. We're going to talk about what it is and what it means and where we need people. But the bottom line is we desperately need to hire people. And so I hope I can get a few of you interested in it today. Thank you for the wonderful introduction, which I definitely can't beat. Anyway, my name is Leslie. It's nice to meet you all if I haven't met you before. I'm a digital forensics and incident response professional, and I've been doing that for quite some time, around 15 years, in IT much longer. Yes, I retired Air Force Reserve. And my current job, I work for a company called Dragos, and I specialize in incident response on industrial control systems. So what that means is when an industrial control system in some type of critical infrastructure like power generation, water treatment, things like that gets hacked, I'm one of the few people on earth who goes out and tries to figure out what happened and what to do. So very much firefighting, cybersecurity work. And we focus pretty much exclusively on critical infrastructure systems. So that's what I do. And I teach classes on this stuff. So I'm definitely condensing some of my coursework in this lecture. I'm taking things that are days or many hours long and condensing it down to 50 minutes for you all. So this will be high level, but hopefully it gives you some places to start. So here's the problem that we're facing in my industry right now of industrial control system cybersecurity. These critical systems run civilization. They keep things like our power on, our water coming out of our faucets, our logistics and supply chains working, things like that. And a lot of things that we don't think about until they're not working. A lot of those systems in modern society rely on industrial control systems. And we'll talk about what those look like. But the bottom line is a lot of those industrial control systems are increasingly digital, computerized, and even more so, increasingly network right now. So they're getting plugged into enterprise networks, they're getting plugged into the internet. And once there's some connection to a device, some kind of digital connection, then there's always pass-through potential. So things are having more potential links out to the public internet and to insecure systems, et cetera. And that's problematic for a lot of reasons. These are very critical systems that are doing important parts of society. And in terms of the people who can actually do the security, the response, the investigations about what's happening to these systems, it's pretty limited because this is a very different space than IT incident response, IT cybersecurity. And something I want to get across to you in this lecture, and again, I only have a few minutes with you, is why it's different. and what the differences are, because you're going to have to approach cybersecurity very differently in this space. And that's incident response, that's penetration testing, that's exploit development, vulnerability research. All those things are different in this space of industrial cybersecurity. So people need to be kind of specialized in it. And it's hard to find people who are willing to do that because there's a lot of challenges in this space, and it requires learning a lot of new novel things that they don't teach in the typical cybersecurity curriculum. So what are these industrial control systems I'm going on and on about? Well, a lot of you are assuming that they're computerized systems. When you think about an industrial control system, you think of a PLC, like a ruggedized computer that's running this stuff, but that's not necessarily true. Industrial control systems have existed for hundreds, if not arguably thousands of years. They can be mechanical, so they can be gears, pulleys. They can be simple analog devices like they were for very much of the 20th century. So just simple electronic inputs instead of digital devices. So all those things are still controlling industrial processes in an automated way. They exist all over the place. We see them in power, water, oil and gas, electric distribution, generation, transmission, also in logistics. There are industrial control systems controlling trains. Think about that one for a minute. Your logistics processing for getting things shipped just in time to places. We've had some trouble with that lately in society, and we, again, don't really notice these things until they go away. So all those things require industrial control systems. And yeah, so these digital industrial control systems, they're increasingly connected to things like local networks for a multitude of reasons I'll tell you about, but they are increasingly connected and drastically increasingly connected. This kind of preceded Internet of Things. So this has been happening for a while now. They've been plugged into stuff more and more for the last 15 to 20 years. And now we are at peak connection. It's kind of gotten out of control, but there are real rational reasons why this stuff is happening. So a lot of these devices, though, were designed in the 70s and 80s and early 90s, and they were not designed to be connected to stuff. We're just tacking that on. So they weren't designed for the security necessary to be piped over insecure networks, over Ethernet, things like that. We're encapsulating serial protocols, things like that. They weren't designed with that kind of security need in mind. So that's problematic, definitely, but necessary in a lot of cases. And industrial devices often remain insecure for logistical and technical reasons. So it's not just people being stupid. I know that there's a propensity right now to think about plugging these power plants into the internet, and that's not exactly what's happening. They're doing this for reasonable, logical reasons, often logistical and cost-saving reasons. And also, this has to do with the long life cycle of these systems, and we'll talk about that as well. But there are real reasons why they are remaining insecure and they're getting interconnected to things. That's not necessarily stupidity or negligence. It has to happen for a variety of reasons. These systems run global civilization. Our company motto is safeguarding civilization, and that's not like an exaggeration or a joke. These systems keep things running. Like we're used to what to do when the power goes out in the Midwest. We all know to have, our flashlights and how long we can have stuff in our refrigerators, things like that. That's kind of normal. But what we're not used to in the United States, for the most part, is like water not coming out of our pipes, or sewage systems not working. Like these systems are so critical to our daily lives, and we never think about what would happen if they didn't work. So bad people know this, though. They do think about that. They do think about what impact it would have on society if all of a sudden we no longer had, clean water or proper sewage disposal, things like that. They do think about that. So we need to think about it as security professionals as well. And what do those threats look like? Okay, so threats that that I have to deal with as an incident responder all the time in industrial networks. Well, first of all, there's the insiders. Arguably the first industrial cyber attack. And this is arguable, but it was in 2000 and it happened in Australia. It was, this is long before Stuxnet or any of that stuff, before the Aurora generator tests, any of that stuff. In Australia, there was a fellow who worked at a a water treatment facility, and he dealt with sewage treatment. And he was a contractor at that facility, and he really wanted to get hired on full time. And he knew the systems really, really well. He knew how to tamper with them, and he knew how to make them do things. And one day he found out he was not going to get hired on full time. And most people would just go, gosh darn it, that stinks. But what he did was he went outside with his remote connection tool, and he dumped a bunch of sewage into a water reservoir. It was a big mess, and it made the news, and people kind of didn't notice it at the time because we weren't thinking about things like Stuxnet. But that's arguably like the first major industrial cyber attack that happened. And why did it happen? Because the insider knew exactly how to break things. Industrial systems, as we'll talk about, are complex. Making them do specific things requires knowledge, but insiders really know how to do that. And the majority of people are decent. I firmly believe in the world, but there's always a few people who are willing to just cause chaos or get revenge, by any method they see necessary. So definitely happens. About a third of the cases that I deal with are insider based. Then there's the commodity stuff. So commodity malware, things like ransomware typically today. Any network can be a target for this stuff. But the people who do ransomware distribution aren't dumb. So they know what networks are likely to pay up, and things that have like critical infrastructure utility in the name, like they think those are probably a pretty good target. So ransomware can definitely impact industrial networks, not for the reasons that the general public typically expects, but it can cause like loss of control and loss of visibility situations, not so much as, like impacts on low-level industrial processes. We'll talk about that as well a little bit later on, but ransomware can definitely have an impact, intentional or unintentionally. And finally, there's the advanced adversaries. So these are the state-style groups or terrorist group, hacktivist groups who have quite advanced, sophisticated resources. They have time and money to throw at things, and they want to do bad things in the future potentially. So most of this is sabotage and espionage based, and it's pre-positioning typically for future attacks. And we need security programs for this stuff. Y'all, we really do. Right now, a lot of what the cybersecurity landscape in these industrial network looks like is just trying to tack it on to the IT cybersecurity people and processes and things. And that doesn't work. This is a very, very different space. We need security programs that are targeted and dedicated to these things. Even if it's an integrated group of people or facilities, we still need to think about these in a discrete way. We can't ignore them. They aren't going to go away. These things keep getting connected to networks, and they keep being targeted more and more by more well-resourced adversaries. And there's a lot of false assumptions about these systems and why they're insecure and what that means and how to secure them. I'll talk a lot about those assumptions and what the reality looks like, but those false assumptions really give us big problems in doing cybersecurity in the industrial space. And this stuff just doesn't fit into an IT box in general. It's very, very different in terms of needs and consequences as well. So I'm throwing out a lot of words here. I want to give you a quick primer about terms that I'm using. So first of all, the term OT means operational technology. And we kind of use that to distinguish IT, so information technology systems, the stuff on the enterprise stuff, from the stuff in the industrial environments. You will not see like industrial operators using the term OT. It's a term that we as cybersecurity professionals and IT professionals use to distinguish the two, but we do use it frequently to differentiate the industrial stuff in its network from the stuff that's in the enterprise network. Industrial control systems, once again, these are not necessarily computers. They can be gears and pulleys. They can be mechanical. They can be analog devices. They were for many, many, many years. And they still sometimes are. There's plenty of mechanical and analog industrial control systems out there today. They're all over the place, sometimes in the same networks as digital ones. ICS, for that reason, is not interchangeable with SCADA. We'll talk about SCADA a little bit, but SCADA is overarching process control. It is not interchangeable with industrial control systems, which can just be a series of gears that make things happen when they're supposed to happen in a process. So different terms there, really important distinction. When I talk about operators, so the operators are the people that are sitting there watching and monitoring and manipulating the industrial process. They're trained, skilled technicians, and they make sure that things are working properly and that the process is happening as it should in the industrial environment, whether that's power generation or making widgets, whatever. And then there's also engineers, so process engineers on site who are things like chemical engineers, electrical engineers. They're specialists in specific technical areas of maintaining the process and the process equipment. So oftentimes they're the people who are managing and updating these industrial control systems. Okay, but I keep talking about processes too. So what are these processes? So processes can be all kinds of different stuff. There are a series of discrete operations which accomplish a physical task. And that could be, again, all kinds of different stuff. It could be making widgets. It could be canning tuna. It could be generating electricity. It could be making a train go and stop at the proper time. So oil and gas, pumping water, things like that. They're all industrial processes. And sometimes processes have sub-processes, right? So like there's a lot of stuff that goes into, say, canning tuna. You have to put the labels on the cans and you have to dump the tuna in the cans and stuff. So the processes can have sub-processes as well. So the overarching process, though, that's the thing that you are doing that's physical in your environment. And processes are made up of process loops. I want to introduce this concept to you. It's going to be very familiar to the electrical engineers out there who I know are present at Purdue, but I apologize to you all. You've seen this before, but I need to explain it to everybody else, okay? So process loops, they consist of 3 components, okay? So first of all, there's a sensor that's checking what's going on with the process. And then there's an actuator that makes things happen. It makes the conveyor belt move, or makes the pressure go up, or makes the temperature go up, or whatever is happening physically in the process. Makes the door open and close. We'll talk about these. And then finally, something has to make decisions about what the actuator does based on sensor input. And again, this can be mechanical, it can be analog, it can be a computer. But something has to make decisions about what's happening in this process loop based on the things that are happening in the sensor and the actuator. So some examples of the stuff. So sensors could be looking at temperature, pressure, motion, or light. Your actuator could be a motor, a pump, a switch, or a valve. And your controller, again, it could be mechanical, it could be an RTU, it could be a PLC, it could be an Internet of Thing device. All kinds of different things, analog and digital. So a very, very simple process loop. For those of you who are not familiar with process loops, one of my favorites is these spinning revolving doors. I think everybody's probably seen one of these. I know we spend a lot of time locked in our house for the last couple of years, but just in case, simple process. So when you walk into these automatic revolving doors, you get into the door and hypothetically, it starts turning, right? It starts turning and you walk through it and then it stops turning, right? But it has to make some decisions, right? So it needs to know when it's supposed to rotate and when it's supposed to stop rotating. Like, the sensor is picking up a few different things, because I'm sure you've noticed if you've gone through these doors at some point at the airport or a hotel, if you get too close to the door itself, physically close, the door will stop. It's a safety mechanism. Like if you start pushing against it or it thinks that there's something obstructing the door, it'll just stop. And then you have to back up, get out of the sensor range, and then it'll start turning again. So that's a safety feature, and that's getting picked up by a sensor. So is there somebody in the door, and is the door obstructed? It's detecting those two things to make decisions about whether the door should be turning or not, right? And then there's a motor, right? It has to have a motor. That's the actuator. The actuator is turning on the motor that makes the door spin. Pretty simple motor. It just makes the door go forward. But yeah, there's an actuator in there that makes the motor start turning. And finally, there has to be a controller, right? It's making some decisions. And the controller is making decisions based on feedback from both the sensor and the actuator. So first of all, hey, it's checking, hey, does a sensor say somebody's in the door? It keeps checking that every second or so. It says, hey, is somebody in the door? Hey, is somebody in the door? And when it says, yes, somebody's in the door, based on that feedback from the sensor, the controller says, hey, actuator, start the motor turning. But It's checking some things from the actuator too. It's checking, hey, actuator, are you spinning right now? Hey, actuator, are you obstructed right now? Is there something in your way? So it's making decisions based on feedback from both of those things. So really simple thing that we see all the time in our daily lives, but it's actually got kind of a complex process loop going on that's making decisions about what to do to keep you safe. You don't want to get banged in the face by the revolving door. So that's what a process loop looks like in something that we see all the time. Now, in any process loop, there are 4 potential things that can go wrong. Okay, so bear with me here. This is any process loop with these 3 things in it. So first of all, the first failure state is the actuator fails to start when it's supposed to. So think about your revolving door. What happens if it fails to start when it's supposed to? Well, you're stuck standing there annoyed, the door isn't turning. Okay, annoying, but nobody's dead. The actuator fails to stop when it's supposed to. So this is, there's somebody in the way of the door and it just keeps going and you get banged in the head. So there's actually a surprising number. When I made this slide, I actually looked up the statistics. A lot of people get hurt by these doors every year. It's actually a significant number of Americans get hurt, minor injuries from revolving doors every year. It's kind of wild, but yeah, it fails to stop. You get bopped by the door. Actuator starts too early or too late, kind of a similar problem there, but the door starts turning a little bit too early or it stops turning a little bit too late. Again, you could get bopped in the head, it could be annoying, things like that. And finally, the actuator goes on for the wrong period of time. So maybe the door just sits there and spins for an hour. I mean, that's annoying for your heat distribution in your building. And it's kind of freaky for the people trying to get through the door. So these conditions, they apply to any industrial control loop, okay? So the door is not a very dangerous thing, but think about something like molten metal in smelting or something. Then these things start becoming much more serious. So when you're thinking about these control loops and you're thinking about the impacts that a malicious person can potentially have on them, any kind of malicious person, insider, commodity, or targeted attack, it's going to be one of these 4 things in a process loop. Basically, they all break down to this. These are the conditions of failure that can happen, and those based on the process and what you're dealing with can be very, very, very severe, especially as a holistic process. Because guys, what an actual industrial process normally looks like is not a simple control loop. What it is a ton of control loops that are all working together. So think about your I love tuna canning plants for some reason. I always use this example. I don't know. I have like 12 talks on YouTube where I talk about tuna canning because I don't know. I think it's just a good example of a complex process that's still understandable. So you have to have like the cans go down the conveyor belt. And then you have to have another process that dumps the tuna into the cans. So those 2 processes have to work together, right? Because if they're not synchronized, like, yes, you have 2 process loops going on here, but like, if they're not synchronized, then you're dumping tuna on your conveyor belt. It's kind of gross. Like, so you want those to be synchronized. So what we've had to do is build overarching systems, either human or digital or mechanical, that synchronize all the different process loops that we have. And we've gotten much better at that with digital systems. So now we have things called distributed control systems. Those came first, that synchronize process loops with a digital system. Or in a much more sophisticated manner today, we have SCADA systems. And again, these systems exist to synchronize a bunch of different process loops without an excessive amount of human intervention. So they make decisions about how all these loops are going to work together to do an overarching complex process. So that's where like SCADA comes in. That's where distributed control systems come in. They're synchronizing all this stuff, okay? And yeah, real life processes, they're complicated. A lot of stuff has to work in synchronization. There can be big safety implications if it doesn't, or process efficiency problems. And what that means is these environments are really complicated too from a digital perspective. So there's oftentimes a lot of different network protocols in place. And that's even in the most simple modern industrial environments. There's a lot of stuff going on. And that means a lot of different vendors and devices exist as well too, doing different stuff. So how do we map this all out? So if you learn the hello Purdue, if you learn nothing else from this lecture, I'm going to introduce you to the Purdue model of referencing industrial system makeup. So the Purdue reference model is an academic model to show you kind of how these systems are laid out, okay? Again, academic models, they are not always precise. They do not reflect all reality. There's always exceptions, but they give us an idea of what this stuff looks like, right? Like the OSI model. Yeah, so the Purdue model is broken out into levels. And essentially at the top, it's your enterprise network. It's your normal IT stuff that we are also familiar with. And then you have, hopefully, some kind of DMZ that separates your enterprise network from your OT environment, your industrial environment. And beneath that, and you have decreasing level numbers that get more and more industrial specific. So at your very lowest level, your level 0, you have very simple analog sensors, things like that, relays, instrumentation, things like that. Very, very simple analog devices, typically, electronic devices, things like that. And then the level above that, you have the control devices. So things like PLCs, so the simple ruggedized computers. So very, very different than your IT computers. At level 2, you have a little bit more familiar stuff. So that's where you have like your operator workstations where they sit there and monitor the systems, monitor the human machine interfaces. So a little bit more familiar stuff there. We start having Windows there, usually older versions of Windows. And then above that, we have like the engineering workstations where updates and patches are done. We have our reporting and scheduling devices, our historians, things like that. So more familiar servers up at those higher levels. Passing into the DMZ, you know, things sometimes have to come in like patches and things or remote access, and then up into your enterprise network. That's the Purdue reference model. Again, at all of these levels of the Purdue reference model, there are different protocols. There are different device manufacturers, different device types, and they all need to be there and they all need to work together. So that's a pretty big attack space, right? From a cybersecurity perspective, like this is a bunch of different protocols you have to think about. And, but fortunately the adversaries do too. This is a complex thing. Again, your process is complicated and there's a lot of different stuff that goes into making it work. So do you think about the industrial control systems that are around you when you're in, say, a corporate environment or an industrial environment? First of all, they often exist in like different places on your network. So they may be in a different VLAN that you don't normally see. There's usually that DMZ separating them from other stuff. So they might be kind of out of sight, out of mind. But they're typically not air gapped. I like to say air gapping is a lie, unless you're in very, very sophisticated like government environments or nuclear environments. There's almost always some crossflow across that DMZ for a variety of reasons: remote access, remote telemetry, patching, updating, services provided to the industrial operators. So air gapping, we don't see much of it. I see maybe 2 or 3 environments in a year that are actually realistically air gapped, and I do this professionally full time. But these environments perform really important tasks that are critical to your operations in a business. And they're oftentimes not considered in like cybersecurity risk modeling because they are, again, kind of off in their own space, managed by their own teams. And there's a lot of fallacies that play into that too. Like we hear that they're too sensitive to assess. So we can't do penetration testing. We can't do red teaming, things like that. And there are limitations there, but that's not true. We can do different types of assessments there. They have to be done differently. They have to be handled differently because we can't just go out and scan our sensitive low-level industrial devices. But there are ways to do that. And we can't just hand wave it. We can't just ignore it because adversaries won't. There's unfamiliar protocols too. That can be daunting. We don't know these protocols as IT cybersecurity people. Like, what is this Modbus thing? What's DNP3? We haven't seen those before, even if Wireshark has dissectors. So that can be daunting. And the devices, of course, at the lower levels of the Purdue model can be unfamiliar. So people try to avoid them for that reason. And oftentimes there's this really unhealthy culture between the industrial operators and cybersecurity professionals because there's years of animosity built up because the IT cybersecurity people haven't been to this lecture and they don't understand the differences between the two and why those differences are important. So 7 misconceptions about industrial cybersecurity. So these are things that I want you to get out of your brains, okay? Because you know, as you go work in the corporate world, if you don't already, you are going to see these things brought up again and again. And I want you to just get them out of your brain right now because they're not real. So the first one is ICS is an edge case. No, it's not. There's probably more industrial devices in the world than there are PCs. They're all over the place and they run critical parts of society. And we need to think about them as cybersecurity professionals. And that it has to be out of scope for scans, pen tests, and assessments. No, you just have to know how to do them right. You can't just ignore them anymore. This is too prevalent. It's too important, too critical to our operations and to our society to just say, we're just going to ignore it when it comes to scanning. No, you can't just send your IT vulnerability scanner after these environments. It's going to blow something up. However, there are strategic ways to do those types of assessments, do that type of scanning, and it needs to get done. So you have to build that knowledge base of how to do stuff in industrial cybersecurity because you can't just hand wave it away. That it's arcane and requires specialized training to understand. You need to understand some things about OT cybersecurity to do it, yes, but you don't need to have a degree in it. You don't need to have specialized in process engineering to do cybersecurity in a process. It's something you can learn. And it's something you can learn by yourself with self-study for the most part. So it shouldn't be something you're just avoiding. These environments, there's an assumption that they're protected by stuff like air gapping, data diodes, and segmentation. And that's not always the case. Air gapping, as I said, is incredibly rare. Data diodes are also incredibly marketed, but I hardly ever see them actually in use. Those are unidirectional data transfer devices that only allow communication one way. Cool idea, but I hardly ever actually see them practically deployed. And segmentation, it's hit or miss. A lot of industrial environments, the firewalls and the DMZ are kind of Swiss cheese. And a lot of times there's no segmentation inside the OT environment itself. So everything's flat. So yeah, don't make assumptions there. Is it that it's purposefully neglected for security? No, we just have to do security differently there because the requirements are different. Could easily be secured using modern security tools. No, that's not going to work. We just looked at the Purdue model, the low levels, you're not installing EDR on any of that. It's not going to happen. You're not necessarily even doing that at the high levels of your industrial environment. We've got to use different tactics here. And it's vulnerable simply because individual devices are insecure. I see a lot of researchers just going out on Shodan or like investigating a particular PLC and saying, hey, this is super vulnerable, the world is ending. Industrial devices are part of a holistic process in a network. And the fact that one PLC is potentially vulnerable does not speak to the overall risk posture of the entire processor, the entire network. Because again, we've got a bunch of processes working together and a bunch of different control devices that are making sure they do the right thing. So one PLC malfunctioning is not necessarily going to cause any impact at all in the entire process. So we can't think about these industrial networks in terms of individual industrial devices. So some real facts. Here are some real things that you can learn about these industrial environments. So first of all, industrial cyber attacks are increasing. I have a lot of incidents coming in. This is a real thing that's happening, even if you aren't always hearing about it on the news. ICS are often based around legacy and hardware and protocols for a reason. Industrial life cycles for equipment are very long. And when you buy an industrial system, you buy it like you were buying IBM in the 1970s. You buy everything in the Purdue model as one package. So you can't just replace one part. You're going to get out of warranty. You're going to lose your support contract. And you're probably going to make your industrial process fail. So you buy them for like 30 years. And you have maybe like major vendor updates every 15 years or something. So very, very long life cycles for this stuff for a reason. That's how they are designed. Familiar IT tech is becoming common. We call that IT-OT convergence because it's cheap. Because why would you build your own custom switches for industrial when you can just go buy Cisco or Juniper or something? Why build your own HMIs when you can stick them on top of Windows XP embedded? It's just cheap. So they're going to do it. Of course, they're going to do it. It's going to happen. TCP/IP is increasingly common for the same reason. Why would they write their own protocols to do data transfer? It's costly. Why do that? And it's inefficient, and they could break more things. So air gapping, again, pretty much never see it. When people tell you something's air gapped, go physically look at the cables to see if anything's plugged into it. They're going to say it's air gapped because that's a good thing that you say about your industrial environment. And then you're going to see it's plugged into a firewall or a modem, and there's plenty of data transfer going into that environment. ICS protocols rarely have authentication or encryption for a reason, because they need to be quick and efficient and never fail. They are doing things like making sure you don't die, making sure that the facility doesn't catch on fire. You start sticking a bunch of security on top of that, there is more potential for failure, and there's more potential for latency, for data loss, things like that. These protocols need to be quick and efficient, so they are unencrypted for a reason. Now, there are some higher level industrial protocols that are starting to be encrypted, but a lot of the ones that aren't, they are not for a reason. ICS technology can be sensitive to scanning and exploitation, but there are ways to test it. Some good tactics there are to use like the system when it's down for maintenance and test it then. Sometimes people have a digital twin of their environment. So if they have a bunch of power plants, they have a fake industrial control system, like they buy an extra one and they use that for testing their patches and doing vulnerability assessments, things like that. We call it a digital twin, a digital twin. So there's potential there to do scanning properly. There's also passive assessment using packet captures. You can do a lot of vulnerability assessment doing that. So there's ways to do this stuff. And yes, it is sensitive. Don't go out there and scan your industrial network, but there's strategy behind it. You can assess them. Operators have a completely different and usually correct priority about everything. Yes, they are worried about the process working and people not dying. Very important things. I think we can all agree that these are good priorities, right? So that is what the operators are typically thinking about. And maybe we should do more of that as cybersecurity professionals. It's good risk management to think about what are the things we really care about? What would a really bad day really look like for us? So we can learn a lot from that. And ICS is comprehensible, and we must identify, learn, and secure it in our environments as we go out and we work in the workforce, as we are doing research, as we are learning where we want to be in the cybersecurity field. This is important stuff, and we can understand it, and we can make an impact, but we have to go about it in a strategic way. So why is this convergence between IT and OT happening? Well, I talked about this already. I kind of beat this horse to death already, but yeah, it's cheap. It's accessible and it's cheap. Industrial operators want to do things efficiently when they design systems. So of course they're reusing things like Windows, like TCP/IP, et cetera, using commercial networking equipment, stuff like that. Reinventing the wheel just adds more potential points of failure. And it's a lot easier to replace parts too when stuff breaks. They can just order more stuff from Cisco and ship it off to you as their branded network equipment. So yeah, it's going to keep happening. We're going to keep seeing this convergence, but again, this makes the OT devices more vulnerable and understandable to adversaries, to people who are doing bad stuff. And why is it being networked at all? Why don't we just not network it? Why don't we just not plug it in? Well, first of all, there's the problem of operator and technician remote access. So we had this big pandemic thing, if nobody noticed, but even before that, even before we had to do all of our work remotely, I mean, just logistically, like a lot of industrial facilities are in really remote places. If you want to go out to like an oil refinery, an oil rig on the water, you need to go to like water survival training first. So if you want to go out to the oil rig, you have to learn how to survive a helicopter crash. They drop you in a NASA-sized pool and in a upside down helicopter frame, and you have to swim your way out. Like that's what it takes to just go out to an oil rig and replace a computer or something. So of course we want to be able to have remote access to things. It can be logistically and safety wise complex to go out to these sites and do things. So remote access is a really huge boon. It makes things more quick and efficient, more people can access a system when they need to, but of course it makes them more accessible to adversaries as well. This reduces costs as well. So, you can just centralize your workforce, centralize your operators instead of having people at every single power plant. You just put them in a central location. So there's a lot of good reasons to have these devices networked. It's cost saving, but it's also efficiencies, it's logistics. I mean, if you have something that's so remote that you cannot physically get a technician to it, the system's just going to fail or go down if you can't get somebody out there. So really good reasons to do it, but it makes things more vulnerable. It's a trade-off. There's also things like telemetry. We get a lot of process efficiencies by being able to monitor how processes are doing to a granular level all the time. And yeah, I mean, that saves money. It makes our processes more effective, more environmentally friendly. So there's a lot of reasons to internetwork this stuff. And why don't we just air gap it all? Well, for the same reasons. We need that remote access for a variety of reasons, and air gapping becomes incredibly expensive because all of a sudden we have to have boots on the ground, trained, safety prepared people go out to these facilities to do everything. There's usually some connectivity required, and things like data diodes are expensive. We hardly ever see them. And even if you air gap things, there's the human sneaker net thing coming in to do updates. People are bringing in laptops, USB drives, modems, things like that, because they have to be able to update things and modify them. So really don't see very many of those. So why is there so much legacy stuff? Yeah, we see a lot of stuff like XP embedded, yes. And I mentioned previously that we have these really long life cycles in OT networks. And that's again, because you buy systems as a package and you buy them to use for decades. Okay, so they are in each part of this Purdue model, it's interdependent on the other levels, on the other devices. And you take one piece out and you replace it with something else, things don't work right anymore. And your number one concern again is the safe operation of your process. And manipulating how the devices are configured, replacing devices without vendor input can make your process unsafe. That's when people start dying. So you can't just go in there and replace your operating system on all your Windows devices. They have to do things like talk to the PLCs. And that requires like custom drivers and just like all kinds of stuff. You can't just go out there and put a new version of Windows on them. You can't necessarily put new security tools on them for the same reason. At the very most innocuous, because it's going to void your warranty. And then at the very most severe, because somebody might die. And maintenance windows in these environments are also very, very rare. They're sometimes maybe every year or every 6 months. Those are the only times these processes will be brought down for actual system maintenance. So you could go 6 months before the process can be shut down in a way that you could do an assessment or do patching, et cetera. So that's very normal. That's how these systems operate. And we have to work around things like that as security professionals. And to do security, we really have to be adaptable in these environments. So we have to understand all this stuff, and we have to be willing to figure out ways to work around it. Okay, we can install EDR, but what can we do? How can we possibly passively monitor the network? You know, go out there and just pull data off a span port, look at packets, and detect malicious behavior that way. That's not impacting the process usually. So we can do that maybe instead of installing EDR or the modern security tools that we're used to. In terms of forensics, maybe we can pull a system out of production, maybe we can't. We're just going to have to adapt. Because again, safety and the process come first. So the threats that we're facing, I talked about the 3 types of attacks that we're facing in general, and the 3 types of things that I typically respond to as an incident responder. But in general, these cyber attacks are on the rise. They're increasing every year. My team is growing every year because we face more and more cyber attacks against industrial systems that are effective. It's true that targeted attacks against industrial systems, so like shutting off the power to a facility or, you know, making the water stop flowing or contaminating the water. Those are generally more resource intensive things because as I mentioned, and I showed you previously, industrial processes are complex. There's lots of levels in the Purdue model, and then there's lots of process loops going on in these processes. So to understand how to make a specific thing happen in them, you need to understand a lot about the process, right? You need to understand what protocols are in use, what devices, how the process works, how the different loops work together, what happens if one fails. So you need process engineers, you need experts on the industrial control systems, and you need a lot of reconnaissance to make a specific thing happen reliably. Now you can just go in and smash things, and maybe it'll do something, maybe it won't, but it will probably blow your cover. People are going to notice that you're in the network and they're going to kick you out. And that happens. We saw that with Oldsmar. Sometimes people just poke at stuff. They got caught. The operators noticed. Their process controls worked properly in that case. But yeah, I mean, targeted attacks against these systems continue to be expensive because you need to have resources and spend time learning about the target networks. But what we see now, and what we've seen for several years now, is these resourced adversaries gaining reconnaissance data about the networks that they might want to target in the future, because they know it's going to be resource intensive to do something. So what they do is they get into the industrial network and they start taking screenshots. They start, examining documents and configuration files in the industrial network, and they start pre-positioning. They have a foothold and they're gaining knowledge about the network. So if in 2 years they want to do something really bad, it'll be easy peasy because they know. They've been there, they know the environment really well, and they're ready to go. It's expensive, but these types of adversaries, the advanced adversaries, they have the resources to do that, and they have the reason to do it and not be detected. The commodity malware is still a problem. Again, that's kind of the maybe it breaks something, maybe it doesn't smash kind of scenario, but ransomware can be very impactful on the higher levels of the Purdue model. So those HMIs that display the system status, the engineering workstations that are used to do maintenance of the system, those are usually running Windows. They'll be impacted by ransomware, and they will have an impact on operations, even if it's, wow, we can't see what's happening in our process anymore, we better shut down. So it's not necessarily the PLCs being tampered with in that case, but hey, we can't see if the system's running safely anymore, I guess we better stop everything, is still an impact to operations. Unfortunately, reconnaissance and the stuff that is really quietly happening in the background, it doesn't really build security budgets. A lot of organizations are just starting to do cybersecurity in their OT environments, and they don't know yet that somebody's had a foothold in it for 5 years already, and they've done intense reconnaissance. So if people aren't looking for that, if they haven't investigated it, it's not like ransomware. Nothing's popping up on their screens. Somebody may have been in their network for a long time, pre-positioning for a future attack, and they haven't been increasing their security budget because there's nothing to take to their executives. So there's a lot of challenges there. These low and slow type of attacks don't get attention of executives. So yeah, there's a lot of problems out there. And that's why we really need you. We need people to do a lot of different things in this space. So we need people to just go out and work for these organizations and do good cybersecurity with an understanding of these OT needs. But we also need people to do research into potential threats. So research into device vulnerability. So what can be done to PLCs? How can they be tampered with? How can we do forensics on them in the future? How can we improve our forensic processes? And then threat research, so threat intelligence, who's out there doing what? There's a lot of ground to cover there because there's a lot of industrial verticals and they're all different. So who's targeting medical stuff and what are they doing to that? There's always more questions to answer there, and there's not a lot of people in this space. And in terms of IT-OT convergence, it's just increasing and increasing and increasing. So here's some key concepts. If you're thinking, hey, this sounds really interesting and really cool, I've given you some facts and some fallacies, but if you want to learn more about this field, if I've whetted your appetite and you're like, hey, I'd like to maybe be a part of this OT security research stuff. First of all, it's a huge landscape. Water is totally different than power generation. So different spaces. It's a vast landscape. So just like cybersecurity in general, you're going to have to focus and make some decisions about what matters to you. You need to understand that consequences and mitigation are very important to processes. If it doesn't actually have a consequence to the process, like life and safety or process impact, it might not matter to the operators. And we're always trying to mitigate potential consequences. So you might find something that looks really, really bad from a cybersecurity perspective. And then we actually look at the holistic process and everything happening in the Purdue model and say, okay, but that can't possibly happen because there's a physical safety control that's preventing the place from going on fire. or preventing the pressure from getting too high. A valve will open and the pressure will release. So nothing bad will actually happen. So we need to understand these potential industrial process consequences and the mitigations that are in place. We need to work with the process engineers. They're always going to be the senior experts on how the process works. We can't just ignore them. We're never going to know how to do their job better than them. And learning about any process, so pick one, any process will help you understand how processes work and how they're laid out and how their networks work and how we model consequences and mitigations. And it's fine to start with something familiar. Everybody has hobbies. Everybody's had other careers potentially or other degrees in the past. And there might be a particular industrial niche that interests you, and that's fine, start there. But most importantly, be adaptable. You have to adapt to the fact that the process comes first and life and safety comes first before cybersecurity or anything else. Everything is in terms of keeping people safe and keeping these critical processes running. Some essential things you'll need to learn once you focus down to a niche is the overarching process. Not at a granular level, you don't need to be an electrical engineer, but how does the process work overall? What is happening? What do the process loops look like? How does it flow? And then in terms of the IT side of things, what's the network and system topology look like? So are there routers, switches, VLANs, et cetera? How's it all laid out? And at every level of the Purdue level, what industrial and IT protocols are in use? Again, that changes across the environment and there's a bunch in use. So where do they exist? What talks to what using what? And do those protocols have any security on them? And then finally, device, make, and model and function. So what are the industrial devices in play? What do they do? And when were they last updated? Things like that. To think about mitigations, you'll need to understand the safety controls that are in place. So things like mechanical or physical or human controls preventing bad things from happening. And you need to understand how these sub-processes interact with one another. So again, your process flow, high level, how do things in general work in this process? Again, focus on a vertical or technology, and then you might want to get more granular and focus on a security aspect. So the defense of this device or offense. OSINT, open source intelligence, is really going to be your friend here. It's really going to help you. Things like Google searching, Google hacking, ScribD, the document repository, has a ton of industrial device manuals out there that aren't supposed to be on the internet. And Shodan also shows lots of exposed industrial devices. Don't poke at them, please, but you can take a look at them. Ask questions and be collaborative with your process engineer friends and the people who are studying things like electrical engineering, chemical engineering. Again, they are always going to be the experts at the processes. So learn from them about the high level process so you can start thinking about these other cybersecurity related questions. A great option too, if you want to do device research, is going out and buying things like used PLCs off eBay. They're sometimes maybe a few $100s. So they're not cheap, but they're definitely not in a realm of improbability for purchasing yourself to poke at. Again, learning about these processes, always ask questions of engineers and operators who are actually doing them, shadow them, ask questions, be humble, and let them teach. Everybody likes talking about their job. And understand that you'll never know everything about the process and process engineering, and that's okay. You're the cybersecurity person. You just need to understand what they're concerned about and the process at a high level. And you need to understand that your priorities and vocabulary are totally different than theirs. So you need to adapt. Again, be adaptable. And by doing all these things, you're going to become a trusted partner and advisor because they're never going to know as much about cybersecurity as you know. So you need to work together. Again, the operator point of view, they care about consequences and risk. They care about people dying. They care about process failures. They care about environmental contamination. Those are the things they care about. Don't tell them that there's configure on the network. They don't care. They care about things that are going to impact the process, impact safety, cause consequences that they care about. So just having the network be infected, maybe that's not that big of a concern. Maybe they can leave that for 6 months because it's not actually having a meaningful process impact. Maybe bringing down the network to fix it will cost more. So we need to change our mentality about that. We need to start thinking about things in terms of consequences instead of just cybersecurity stuff in a vacuum. So you need to understand the process and those key consequences. That's the most crucial thing. And then you can work down from there to figure out what systems and conditions could cause those consequences and start looking at the mitigations from a cybersecurity perspective and from a mechanical, physical, human perspective. Again, pick a starting point. Don't get overwhelmed by all the stuff there is to learn in industrial control cybersecurity. Every vertical is different. So again, focus on one. They all have technical differences. Use your OSINT as much as possible and be willing to learn about processes, consequences, and operations. There is some formal training available, but it's limited in scope. So free training, there's Idaho National Laboratories. They have some web-based training up on their website. You can just go do today, which will teach you a lot about industrial cybersecurity. And they'll also teach you about some industrial protocols and how they work, things like that. It's very handy. They also have an in-person course that you can take if you work for an organization that does industrial cybersecurity, like electric generation, utilities, things like that. There's paid training out there too. There's SANS courses on industrial cybersecurity. FireEye has classes. We have classes at Dragos. And a lot of industrial vendors offer courses on their specific technologies as well. So how to secure those. Most of those courses are pretty pricey. That's something that you generally want your employer to pay for in the future, but keep in mind that they exist. But for free stuff, the INL stuff is awesome. Our CEO, Robert Lee, has a blog on his website. He has this blog that has a long list of free and paid resources for learning about industrial control cybersecurity. And it's kept up to date. It's pretty handy. There's some more blog articles, podcasts, things out there, things that he's found useful. And I agree with most of those. But overall, let's review here. Cybersecurity essentials in industrial control networks. Number one is collaboration and communication between IT and OT. You've got to be willing to work with the OT people, even if that relationship is a little rocky because of past miscommunications. Cybersecurity people have to understand the process. You have to take the time to learn it at a high level. Cybersecurity people also have to take the time to understand the consequences of concern. So what is a worst day ever in this environment? Is it somebody dying? Is it the place catching on fire? Is it the machine exploding? What can go wrong that really matters? You also need to understand that a lot of your IT stuff that you take for granted doesn't exist in the OT environments. So things like asset inventories and network maps, they might not exist at all in the OT environment. So they might need to be remade. They're critical, of course, for all cybersecurity, as well as an incident response plan that's specific to the OT environment. Again, different stuff is going on here, different risk modeling. You need to have a separate incident response plan for that environment. Crown jewel analysis. So what systems are critical? Which ones can cause those bad consequences? Collection management. What sorts of logs, sources, security systems, et cetera, exist in that environment that you can reference? And regulatory requirements. There's very, very different regulatory requirements for reporting incidents and doing security in industrial environments. So you need to understand those as a cybersecurity professional as well. Your tools, some things that you can throw at these problems. Segmentation and DMZ control are integral. A lot of these firewalls in the industrial DMZs, again, are Swiss cheese. So very problematic. Access control and logging. So being able to see who logged in when and making sure that it's one single point of entry that's well controlled, hopefully with things like multi-factor authentication, is a huge boon that can really cut down on potential attack vectors. Passive network monitoring, that doesn't impact your process. You're not scanning anything. And you can do threat hunting and detection using it. So that's a wonderful tool that you have at your disposal. Controlling removable media, that's another vector for attack and infection. A lot of those policies that exist in your IT environment probably don't exist in the OT environment. It's a completely different environment. Assessment of digital twin or lab systems. Remember, I talked about sometimes you have a duplicate of some of your industrial systems that you can test safely without scanning your real environment. That's a good option as well if you can afford it. Assessment during outage or maintenance windows. Know when those windows are. When is a system going down for maintenance? That might be a good time to do some scanning and assessment. Securing and monitoring higher level systems. Your low-level systems are hard to deal with. They're very different. Their protocols are very unusual to IT people. Your higher level systems in the Purdue model, however, are things like Windows systems, and you can do a lot with those right now in terms of forensic and analysis and threat hunting, et cetera. So use those to your advantage. An adversary probably has to come down through those. And collaborating with the vendors on enabling feasible security features. A lot of times there are security features that are not on by default in industrial devices. And if you talk to the vendor and talk to your engineers, there's potential to turn them on. If your OT staff is suspicious or wary of you, try to understand why and enforce that you're there to work with them, not audit them. The audit word is the magic word there that makes them run away because they've been burnt so many times. If they're too legacy systemed or tightly controlled for modern security tools, again, think about that passive network monitoring. You can probably do that. If you're having trouble securing anything, try to simply control and monitor ingress and egress. Again, the remote access to your devices. If you can control that, you're doing a lot. You're really cutting down the vectors that somebody can use to get into the environment. If OT people were doing their own shadow IT, don't just take it away. For God's sakes, don't burn that relationship anymore. Try to repurpose their efforts into something else. Because in a lot of cases, it was their kingdom and these IT people are coming in and messing it up. If they are interested in helping you do security, find ways to let them help you do security. Otherwise, you're just going to burn that relationship worse. If you don't have the capacity to monitor low-level devices, understand that most attacks have to come in through the higher Purdue levels. So there's still places you can monitor, even if you don't know how to deal with your low-level devices yet. So with that, I'll answer some questions, I think. What do you all want to know? What have I not beaten to death here?
Thank you, Leslie. We have a number of questions in the Q&A. Okay. We've sort of run a little bit over. You can answer as many of them that you wish, and people can stick around if they'd prefer to hear the answers. So
sure, if you'd like to stick around for some answers, I'm going to answer some of these questions now. If not, thanks for hanging out. I hope you learned things from this talk that are going to be useful to you. I hope I've convinced one or two of you to maybe explore this area for your future career. Patrick, how bad is the legacy system in critical infrastructure? Are we going to be relying on legacy systems until well after they've literally died? Yes, absolutely, we will be. Because again, you're dealing with like 30-year life cycles. If somebody buys a system today, they're going to be using it for 20, 30 years. So they're buying Windows 10 today, and they'll be using it until at least I'm retired. So yeah, that's going to be a perpetual problem because of the long life cycles there. Would open sourcing code bases for ICS management help mitigate exploits? I mean, there's always value in taking a look at the code bases for ICS stuff, for anything in general in critical infrastructure. But again, we're dealing with these holistic processes. So there are a lot of vulnerabilities in individual devices and code bases in industrial networks. But they are already kind of mitigated through other means. So just simply the fact that a single device is exploitable doesn't mean the process is exploitable. Yes, it's good to look at that stuff. It's good to do device vulnerability and protocol vulnerability research, but that's not a solution. It's not a silver bullet solution for these problems because somebody attacking a process is going to attack the process, not an individual device. Can you share the slides? I think this talk is recorded. How does a normal person without ICS experience get some experience without a company backing them? I hope that I answered that in the talk. I showed you some resources that you can use that are free. Could developing custom protocols and operating systems help obfuscate systems? Security through obscurity really isn't a long-term solution. Really, I mean, that's what we did in the past. We had custom operating systems and custom protocols. They make it harder for us to do security as well as harder for adversaries to do things. Again, it introduces more problems than it really solves. We are going the way of IT/OT convergence. It's just going to happen. We are leaving the world of custom protocols, custom operating systems, and we're moving towards, just using standard IT systems for a lot of things. What's the favorite part of my job? Oh, learning about processes. The best part of this job is learning about a whole bunch of different processes and how they work. I mean, I find out about industrial processes I didn't even know existed. Mining for materials I didn't even know were used. So, that stuff is really, really fun. Is a brand new system set up tomorrow more secure than an old system with updated security? Can anything be done to better secure a new system that can't be done to an older system? In general, the newer systems are currently more secure because they're coming out with like Windows 10 instead of Windows XP. And Windows 10 is just so much more fundamentally secure than Windows XP that you can't really equate the two. Now, granted, there's a lot of mitigations in place in a lot of older networks, like human mitigations, process mitigations, things like that. But in general, if you're just talking about the systems themselves, I'd be much happier with a modern industrial system that's using Windows 10 with its basic security features turned on than a system from 10 years ago that they've tried to secure. So if there's nothing else, thank you so much for having me. It was really fun. I hope I gave you some ideas about what industrial cybersecurity looks like and whetted your appetite a little bit to learn more about it. There's only so much I can cram into an hour. So good luck to all of you. Thanks for coming.
Thank you, Leslie. And this talk, as all our seminars, has been recorded and will be up on our website. That's in the chat with the URL. And let me remind you, next week's seminar is going to be on the future trends in cybercrime and hybrid warfare by an expert who's been working in this field for a number of years in Europe. That should be a very interesting talk as well. Thank you, Leslie. Thank you for everyone attending, and have a great evening, everyone. Good night.